Greeting Earthlings! If you follow the channel, you might have seen the short format video that I quickly put together when we got the original Apollo DSKY screen turned on in my lab. Here is the fuller story behind this, and you will be relieved to see that this one will have the camera oriented the correct way. That said, I plead not guilty. It's YouTube enforcing the low resolution and vertical format on their shorts. Like it's trying to imitate TikTok, but did not quite get it, so it copied the bad features instead of the good ones. The vagaries of product specifications in large companies. Oh well, enjoy the clicking. Okay, now that you have suffered the 1-minute short in YouTube enforced potato vision, let's widen our field of view. Ah, much better. But look at this. Yes, folks, the screen is really that good. HD in 1965 contrast up the wazoo. How is that even possible? But before we go there, you might ask, what's a DSKY? Written DSKY, the initials stand for Display Keyboard Interface, and it was the astronaut's interface to the Apollo guidance computer, the computer we proudly restored for the 50th anniversary of the moon landing in 2019. There were two of them in the command module, one on the main panel offset to the left, and one besides the telescope and optics, to enter the star sightings and align the inertial measurement platform, which the computer was in charge of. In the LEM, there is only one DSKY at the bottom of the control panel, easily accessible to the two astronauts, here lodged between Neil Armstrong and Buzz Aldrin. The concept was radically novel, a real-time interface on a glass screen, so you could dialogue directly with the computer, hell, fly a spaceship to the moon. This is Apollo 11, by the way, demonstrating verb 35, which is the DSKY light test, then going back to the idle program P00 by using verb 37 and program 00. And this is the DSKY in Snoopy, the Apollo 10 LEM. I think Gene Cernan is pressing the buttons. The DSKY started its life with the Block 1 revision. In this early DSKY, there were two distinct shapes, the familiar squarish one for the main DSKY on the command panel, and an elongated one for the navigation DSKY besides the optics. This early DSKY already features the electroluminescent number displays that makes it so unique, but they appear to be made of several different little screens at this point, as you can see on this 1965 specification drawing. The Block 1 DSKY has no back shell, so you can see how it's made of individual electronic modules plugged into a chassis, very much like the rest of the Apollo guidance computer construction. But the DSKY you are most likely familiar with is the Block 2 revision. It is the one that was flown in all the manned missions. It is a much more involved hermetically sealed design, like the rest of the Block 2 electronics. It has a hermetic backshell enclosure, and it also has a much improved illuminated keyboard, also hermetic. But foremost, it features the large single-pane electroluminescent indicator, the iconic display we are trying to relight here. You see, in the early 1960s, you didn't have many good options for a numerical display, particularly one with a flat form factor. The lovely Nixie tubes were probably your best option, but they are bulky and really sensitive to vibrations. Indicators with regular lamp filaments were also tried, but fell far short of achieving the desired illumination uniformity, brightness, and thickness requirements. But foremost, the power consumption was far too high. Aren't you glad we didn't end up with this design? Instead, NASA chose to develop an electroluminescent display which yielded a highly legible, bright, and uniform screen that was amazingly thin and low power for the time. But let's see how the whole DSKY is constructed. In 2019, we opened a Block 2 DSKY that was to be offered for sale on our auction. This was done live at our auction's booth during the Vintage Computer Festival. However, we already suspected this was not a functional DSKY, but a model used for thermal testing. And indeed, it is exactly what this was. So Mike is already furiously hacking at it and has removed the black back shell. You can see it on the table and spot the hermetic seal that runs all around the edge. That gave access to the green blocks, which are stand-ins for the actual electronic modules. These are not functional, they only contain a resistive element to generate heat. In this way, they could do thermal testing of the Block 2 DSKY design. Mike is starting the disassembly of the front part of the DSKY. It appears to be made of functional parts, a full keyboard, the warning indicator panel, and our famous electroluminescent display panel. Here you go. And you can admire the modular construction with two equal-sized display modules, one with the warning lights made out of regular light bulbs, and the digital display with its electroluminescent technology. On the keyboard, you can spot the hermetic micro switches under each key. They are the little gray rectangles right under the keys. The large keys have a very long travel with carefully controlled force, so you could operate them with your astronaut gloves on very reliably. On to the removal of the warning panel. As soon as he pops it out, you can see the hermetic seal on the mount, and when he flips the display over, you'll see the Malco pin connectors forming an array at the back. The digital electroluminescent panel has the same arrangement. Sadly, I don't have good footage of it, but Carl briefly held in his hands the electroluminescent display, which also appeared to be a functional unit. But soon we reassembled the whole DSKY, it sold, and sadly we never got to see the glow of the mythical display. But of course, having a functional DSKY was essential for our restoration work. There are many amazing DSKY replicas out there, my favorite probably being this Lego one, and this commercial one from Sam Ammons, but none that you can connect to a real AGC. So for the restoration, we took the matter in our own hands. Mike made a fantastic virtual one in his AGC monitor, which was our mainstay during the restoration. Then Carl made a functional replica based on an LED display. We even used it to do simulated landings on the moon once the AGC was repaired. Picking up some dust.
7 feet. 0. That's not bad. We're falling through the surface.
Okay.
Yeah.
It doesn't know when it stopped.
We learned it, guys.
We did. Yeah.
And while we had much fun using Carl's DSKY, we all were left to wonder how the original electroluminescent display would have looked in person. I guess one would have to try to remake one. As it turns out, at about the same time, Ben Krasnow from the Applied Science channel had just produced an astonishing video where not only he explained how electroluminescent displays work, but also he demonstrated the whole process of fabricating his own. You have to watch Ben's video for the full story, but in quick summary, electroluminescent displays are made by spraying a special luminescent paint over a piece of plastic or glass with a transparent electrode, putting a thin layer of insulating dielectric, then forming another contact on the other side. When a high AC voltage of say 300 volts is applied between the two electrodes, an eerie glow is produced. Another breakthrough happened when Mike Stewart and Ron Berkey recovered the original blueprints for the display artwork from the National Archives. I contacted Ben, sent the drawings to him, and wondered if he could possibly reproduce such a screen. He responded rightly that it would be awfully difficult and time-consuming, and I didn't hear much for the next 6 months. But I almost fell off my chair when I saw this short video tweet. Then this happened shortly thereafter.
Today on Applied Science, I'm going to show you how I built these custom electroluminescent displays.
Hooray! No kidding! Ben had done it! And shortly after he published his video about it, he showed up in our lab, and for the first time we got to experience our closest approximation to what the DSKY would have looked like. Compared to the LEDs, it has an ethereal visual quality that is really totally unique. But wait, it gets better. Original spare displays are still floating around and occasionally show up at auctions. We knew some collectors that acquired one, but of course, none would let us power them up. That is, until we met Marcel. So Marcel, here's a pièce de résistance here.
So we have description. A Block 2 DSKY EL display. This particular one was from a pre-flight unit. Got a little cracked glass there, but hopefully Carl can get this thing cranking even with that.
So that's a real electroluminescent thing.
Yeah, it should light up with the proper wavelength. And it's got those same pins that the AGC had, so...
Yeah, and we have those made by Samtec, and then we'll lend it to the DSKY master. Carl's going to make it all work.
Make a PCB and interface for it. Or
And just for comparison, this was another spare that was sitting around for a very long time with its original acceptance documents. This was flight ready and qualified and sitting around.
Right. So Marcel not only has one, he has two of them that he is willing to lend to us. The first one is a prototype with some slight damage, and the second one is a flight qualified spare in pristine condition, just out of its sealed storage bag, complete with documentation.
And this is really nice. This is the basically log of this particular device, matching serial number 346, and as they took it out from storage and maintained it, put it back, checked it.
Oh, the whole history of where it went.
This is the earlier ones.
70.
that 9 accumulated hours.
So it worked. Been checked.
Oh, it's 70. Okay, it starts out
The
at
earlier
70.
ones, yeah. So
9 operating hours.
here they say they're re-identified, so Mike had some comments about when they changed the number schemes.
Right.
And of course, that's when the pandemic hit. So Carl went in his lair with his precious displays, and we followed from afar, watching his restoration blog that I will link in the doodly-doo. So first thing, how do you wire this thing up? Fortunately, we had a pinout, thanks Ron and Mike, and we had the wire wrap Malco pins, which had been reproduced by Samtec, which I will never be able to thank enough for their sponsorship. Then you need a source of 250 volts AC at 800 Hz. We had the schematic of the power supply, which was a bit tricky to reproduce due to the last saturable transformer used for regulation. But we did not even have to bother with that, because Marcel had an original power supply module from the Block 1 DSKY. Incredible! And it was mostly compatible with the Block 2 screen, so we were good to power up the Block 2 display with an original Block 1 high voltage supply. Unfortunately, when Carl checked the supply, he observed that it was a bit short of spec. The spikes are fine, actually the spikier the better for EL displays, but the positive side is a bit weak. Nevertheless, Carl was able to obtain enough voltage by overdriving it a little bit, and we considered it good to go. So we're doing pretty good. We have the display, we have the power supply, and now to connect it the same way that they did in the original, we'd need the relays. Lots and lots of relays. In 1965, they did not have transistors capable of handling the 250 volts AC, so they used relays instead, 132 of them. They look similar to this modern equivalent. A Block 2 relay module like this one contained 22 relays packed together, so it took 6 modules to light up a whole DSKY including the alarm panel. And these were not just any relays, they were the special latching kind. So since they didn't have transistors that could switch 300 volts reliably, they use relays, and on top of that they use a relay known as a latching relay, which is a cool one. It's a relay with memory. I have only one in my collection, and it has 2 coils. So here you see 3 pins. I'm going to put this in the common of the coil, and the contact of the relay is hooked up to my Soviet lamp here. with Gagarin looking at us. If you energize the first coil, it turns it on. If you energize the second coil, it turns it off. So this thing has some kind of mechanical memory in it, because I don't need to keep it energized, right? I just give it a little pulse, it gets on, and I give it another pulse, it gets off. So it really solves several problems at once. So it solves the high voltage switching. It also solves the memory. It's included in your mechanical relay, right? If you don't have to refresh anything, it stays there once you have put it in the right condition. And then it solves the power consumption problem, because if you look at here, it only consumes power when you switch it. Then once it's over, it's done, right? So 3 problems solved at once. The downside is, of course, that you need a gajillion billion relays and you need to make them flight worthy, which is not that easy, but they managed to do it. And by now, you guessed it, Marcel also had 2 original DSKY relay modules. His are from block 1, but that turned out to be a good thing, since block 1 relay modules have 42 relays instead of 22 in block 2. So with 2 modules, Carl should be able to light half of the panel digits. Carl started with a prototype display and just hooked up a few wires to the power supply. And it lit up! It lives again! As Carl was progressing methodically, he sent us pictures with the static portions lit up, then a few numbers. But Carl was reporting that the display was not very bright nor uniform. A few of the segments and the program activity lights did not light up, only showing a few hot spots. You can sort of see this in this picture. Next came the task to wire the digits properly to the relay modules, according to the original wiring diagrams. And then at first it's a bit intimidating. There are lots and lots of relays and wires, and each of this dotted line represents 1 module of relays. But if you look at it carefully, actually you figure out that for each digit they use only 5 relays. So you would think you'd need 7 relays to control a 7-segment digit, but not all combinations are valid. So they actually managed to do it with 5 relays, and each of these rows control 1 specific digit. And I wanted to check that relay logic to see if it actually works, right? We don't want we want to be sure this moon thing is not a hoax. So I did it in Logisim. So if you look at the schematic here, the power lines come from the bottom. So 1, 2, 3, 4, 5 go to the 250 volts. So remember that when we trace the schematic, that the line going down are power. So I've named my segment the same as they do. Here is a relay K1, that's this relay, and this one is simple. It just powers on DS1H1, which is segment H of 1 particular digit. So if I do that, doop, exactly, I have segment H that's lit up. So if you look at the second relay, it gets interesting because it powers M. So when it's down, it will be connected to 250 volts, so it will be powered up. Here I have the segment M that's lit up. But if it's off, there is another path that goes here, and it will be powered if K3 is on. So which I have reproduced here. So M is either K2 or K2 off, not K2, and K3. So if I do this, it will also light M over here, and the bottom contact of K3 that lights up F, I believe. Yeah, right, this is F. So it lights up 2 digits, F directly and M kind of indirectly. And you go through the whole thing. K4 is pretty straightforward. It just does J and then some other stuff. And K5 does mainly E, and then some other stuff, and then you find the other stuff through the contact, and you have this, well, N can be lit if it's K5 and either K3 or K4, and similar for segment K. And then I pulled up the, there you go, they give you the DSKY codes, right, on the 5 relay to do a blank or the numbers. And let's see if that actually works. And let's see what happens to get 0. So I do K1, and that's hooked up to just one segment. Then it's K2 is 0. K3 is on. So K3 lights up 2 segments. It lights F directly, and it lights M, as we saw before. When K2 is not on, it can be lit if K3 is on. And then it's another 0. And then K5 lights 3 other segments. This one, and this one, and we get a 0. So let's make sure this all works here. So if we do 1 is easy, it's just 2 direct segments. Then 2, so I get that one to 0, then it's another 0, then it's 1, that just lights up 1 segment additional, and then this one again lights up 3 other segments, that's 2. Let's do 3, 3 we add this. Oh, that's pretty cool, right? It lights up 1 segment and extinguishes another. How does that happen? Oh, you can see it over here. There's a not K2 that extinguishes K. There you go. And then no, and so forth, and so on and so forth. This is 4. 5 is here. 6 is here. 7. How is 7? 7 is 1, 1. Here's 7. 8 is this one. And 9 is this one. So therefore their relay logic actually checks out. So the relay logic checks out, and Carl went on to make connectors by inserting the Samtec NASA spec pins in what appears to be holes drilled in wood. I guess we're not flying this. And voila, relay connector done, same on the panel side, and let the wire wrap begin. And we started to see pictures with actual numbers, program 63, then Carl wire wrapped some more, and we got this gorgeous display. You can still see the limitation of the prototype though, with some non-uniformity. The top of the 6 is not lighting up, and the color appears bluer than the period pictures. We confirmed that this was indeed a property of the early displays that were spec'd for a wavelength of 510 nanometers, which is quite blue, while the flight ones were spec'd for a greener 530 nanometers. At this point, it was time to plug in the precious flight qualified display, and we got this picture. Carl reported that it was far brighter, perfectly uniform, and had the expected greener hue of the 530 nanometer wavelength. Now when he sent this better picture, we were flabbergasted. This is far better than I would have expected for 1960s technology. And finally, it's the end of the pandemic, and with everyone vaccinated, Carl finally brought it in the lab for all of us to admire. And that's the back wiring of the real DSKY, and it's done with the Samtec pins, which Carl wire wrapped by hand, like the original, right? They were wire wrapped too, I suppose. Even Ben joined us for the occasion. He wanted to see the real thing and compare it to his heroic recreation. The fellow next to Ben is Eric Schlepfer, known on Twitter as TubeTime, gifted vintage electronic tinkerer and creator of the famous Monster 6502. It is so incredibly crisp, and it looks completely blue in my camera it's and it's green. It's just not correct.
It's really tough to capture on camera.
Why don't you put yours next to it, and then
we'll see what happens here.
See that one?
See how close you got it.
Note that Ben's display had a great fall and broke during our tour when we showed it to Eldon Hall, the lead engineer for the AGC. The EL glass panel separated from the PCB that had the digit electrodes. Ben glued it back together, but it has acquired a model vintage quality in the process. Oh!
You know, see, I think, so I actually had a spectrometer, and the spec is 530 nanometers peak, and so I was measuring mine with the spectrometer, and the output is, it's actually fairly bell-shaped. I mean, it's a little low-beam. Yeah,
It got a little mottled.
that's what I mean, and so it has that kind of like Fallout kind of, you know, future dystopian look.
And of course, no Curiousmarc video would be complete without a little bit of debugging. We had a few problems left with the screen. One digit was stuck to 0, the plus sign was also stuck, and the computer activity light did not work. Something went wrong with the hairy setup while it was transported to my lab. Cal, unfortunately, had to leave because he leaves for a remote place. He leaves for Florida. He's going to move, so he give us a quick run up on how this board works. And there's a problem right now. We have the O in 1202 is always stuck. Actually, if we turn it on for a second, we should see that it's always at 0. And right now I'm pulsing it on and off because it's not responding. So we have to figure out why the relays don't work, and we have to go through the relay drivers. And Eric jumped in. Your new recruit.
Yes. Well, that's quite a wiring job. How long did he spend putting all that together?
I mean, that must have taken him a while.
Yeah.
Oh yeah, a couple of hours.
Plus, so this guy at the back had 160 wires. 180 wires. Right.
It's quite a few wires.
Right.
Like we're down.
And then, no, it didn't have the block 2 relays, so those are block 1 relays, and then it doesn't have the right module, so it just picked relays. So the way this works is every digit is connected to a bunch of relays, and that's of 5 relays. And these are the relay coils. And so the relays are in banks of 5. And you have one that selects the digit, selects one end of the coil. That's this line over here. That goes to negative, and I think that's one that's not working. And then for each relay you have 2 that you bring to the plus. One to latch it, and one to unlatch it. But the fact that the whole digit doesn't respond means that's probably one of the common to the 5 relays. So we couldn't see anything, so I changed my toggling software to digit that works.
Right here at the top is the road drive signal, and this essentially goes high to select the digit that you're trying to access.
This one, right?
Exactly. And then the 2 signals that we have below here actually go out to the same physical relay, and the top one goes out to the set coil, and the bottom one goes to the reset coil. And so when we flash this digit on and off, first we hit up the set pulse here, the set coil, and then the reset. Set.
Reset. Okay, so what we think is that since the whole second digit is not working, is that guy is not working somewhere. We had a digit wiggle for a second.
So the signal's coming out here, it's just not making it through the wires. So I'm probing at the Arduino end, and I'm seeing that road drive signal at this end of the wire, but not at the other end of the wire.
Because your wire is non-conductive.
It is not being a wire.
I bet you it was a crimp on the end there.
I think you might be right.
It's actually pretty high quality feeling.
There we go. Looks like it's working.
There we go. So you just replace the cable. Okay, that was the cable. So this is the wire that we replaced, and it's not beeping, that's for sure. It goes to the trash can. Usually I would be stupid enough to try to repair the wire, but I won't do it this time.
I'm kind of curious to find out what exactly, I'm going to find out.
And Ben soon did find out what was wrong with that Chinesium wire. We had been had. This was not a properly constructed wire. So guys, can you, you did reverse failure analysis on the bad wire and you found that it's not a genuine copper wire?
Yeah, it's CCA, so this copper-clad aluminum.
CCA?
Yeah.
Copper-clad?
Copper-clad aluminum.
So it's when you don't want to pay the price for the copper?
That's right. But yeah, actually you can get hoodwinked, because on Amazon, if you search for stuff like speaker cable or coax even, you'll find a cheap one, and then it'll say, hopefully they'll say it's CCA. The failure mode is funny, like the crimp is actually okay. The break is in the middle of the wire, which is unusual. It's kind of annoying. I think it's the corrosion that really gets it, because when you pull the thing apart, like there's nothing there, and it's because the aluminum has just turned to powder, and the copper layer on the outside is so thin that it basically just falls apart, you know, all by itself.
It's copper powder just floats off.
But I think what makes it worse is the molding process. So whatever is in the PVC, like mold the wire, gets it worse, even worse. Because I've seen a lot of these where there's like a lot of powder in there.
Think of someone who maybe they're not so good at troubleshooting or electronics, and they build a circuit using stuff that they bought on Amazon or some other suppliers from China, and they don't know it's CCA, and their circuit doesn't work, and they never figure it out.
Yeah, like you say, I had a line cord that was completely open, like infinite ohms. I mean, for a 14 gauge CCA wire, it's terrible.
What would really bother me is not a line cord that's completely open, but a line cord that's like 10 ohms.
It starts getting warm.
Yeah, I mean, you could easily start a fire.
Right.
Yeah, no, it is actually a problem. And when you buy line cords, they never say what it is.
No,
it just
they don't.
says IEC power cord or something. So.
Okay, so we finally got it. We have our 0 working, and we got the sign working finally. It was just an inversion of wire. It was cross-wired with computer activity, which we can make blink, but it's annoying as hell. We have to implement it better. But here you go. So what are the screens, by the way, Mike? So this is P63 1202 error. This I recognize. The next one.
Yep. This is your this is P64, so approach phase angle, and then this is your apogee around the moon. So apoloon, I guess.
Okay, so that's 630509. Show me errors.
Yep.
That is 640624. Show me that's the
LPD angle and time remaining.
So you have to look at through the window at 33 graduation, and you have 29 seconds until you cannot redirect anymore. And that's 61.5 miles off on your orbit of the moon.
Yes, above the moon. Yeah.
So those are sort of real displays, except we don't have enough relays to do the 2 last rows.
Yeah, these are all verb 6 and verb 16, which are all 3 register displays.
So if you guys have relay modules, we would like to hear about it. Click, 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 click. Okay, this is very ASMR. And with all of our digits working correctly, at least the one we could wire with the relays we had, I spent some time adjusting the color balance until I had it about somewhat right. That's true color. It's still not green enough. The camera is just dumbfounded by DEL. It has no idea how to color balance this. Does not know, never been exposed to that technology.
I feel like my eyes don't quite know what to do with it either, because it looks to me super green right now, but it's also looked kind of blue to me in others, I guess, other lighting conditions.
This is a lot closer to the real one. This looks approximately right. For some odd reason, this is so satisfying to watch. Mike and I must have stared at it for a good half hour. So I'll leave you with just a bit more ASMR clicking. See you in the next episode.